to present to you about the chapter 7, which is heat exchanger. Firstly, I am going to explain to you about the heat exchanger. Heat exchanger is a device to transfer heat between two or more fluids. The fluids may be separated by a solid wall to prevent the solution from mixing. I am going to explain to you about the types of heat exchanger. There are many types of heat exchanger. Firstly, shell and tube heat exchanger. This exchanger used for high pressure application with pressure greater than 30 bar and temperature greater than 260 degrees Celsius. Next is plate heat exchanger. This exchanger composed of many thin, slightly separated plates that have very large surface area for heat transfer. Next is plate and shell heat exchanger. Combine plates and shell and tube exchanger technologies. This heat exchanger offer high heat transfer, high pressure and high operating temperature. This is adiabatic wheel heat exchanger. This exchanger use an intermediate fluid or solid store to hold heat and then move to the other side of heat exchanger. Next is plate fin heat exchanger, mostly used for low temperature service such as natural gas, helium and oxygen liquefaction plates. Next is a pillow plate heat exchanger. This type of exchanger used in the dairy industry for cooling milk in large direct expansion stainless steel bulk tanks. Next is fluid heat exchanger used for cooling gases whilst also removing certain impurities, thus solving the problem at once. This waste heat recovery unit. This recovery unit heat from a hot gas stream while transferring it to the working medium. Okay, next is dynamic scrape surface. This type of exchanger used for heating or cooling with viscosity product and crystallization process. Next is phase change heat exchanger. This exchanger used either to heat a liquid, to evaporate it, or used as a condenser to cool a vapor and condense it to a liquid. Is a direct contact. This type of heat exchanger involves heat transfer between hot and cold stream of the phases in the absence of the separating wall. Okay, lastly is a microchannel heat exchanger. This type of exchanger used widely in automotive industry, for example, as in the car radiator.
Hi, have you ever heard about LMTD? Never, right? So today I will share with you about LMTD. So what is LMTD? LMTD is defined as the logarithm temperature difference between the hot and cold fluid passing through the each end of heat exchanger pipes.
LMTD is calculated by keeping some factors in mind, which are types of heat exchanger and temperature of the foreend position, which are inlet temperature of the hot fluid, outlet temperature of the hot fluid, inlet temperature of the cold fluid, and outlet temperature of the cold fluid.
So now I will share with you logarithm temperature difference formula. LMTD equal dT1 minus dT2 divided by non times with dT1 divided by dT2. The formula is different depend on types of flow, which is parallel and counter flow. Okay, so this is the sample of the question of LMTD. In a shell tube heat exchanger, a cold water entering at 30 degrees C and leaving at 55 degrees C in a parallel flow heat exchanger, by hot water entering at 100 degrees C and leaving at 85 degrees C. Find the LMTD. So from this question, we can extract the information first. We need to split find first 100 dBc minus with equal 830 dBc. So we got 70 dBc. And for delta T2, 55 dBc minus with 55 dBc, and the answer is 30 dBc. So we got T1 and T2. So the formula we got from here, we need to substitute into the LMTD formula. LMTD equal to 70 dBc minus 50 dBc divided by 1. So the answer is 47.21 degrees. So this is the LMTD for the parallel flow heat exchanger. For part 2, we will calculate on counter flow heat exchanger. We are going to use the same equations before, and I didn't change anything. So we just use the information from before. Okay, so first we need to write the equation. We use the same like before. Delta T1 minus delta T2 over long sweep. Delta T1 equal to delta T2. Okay. So we calculate delta T1 first. Delta T1 is equal to T hot E minus T cool R. It's different from before because before it's put in, but we change here. You can see the difference. So we just put into the function into the formula. Is 100 dBc minus equal R is 30 dBc. So 70 and add 55 dBc. So we got 45 dBc. And for delta T2, T hot R minus with T cold in. Before it's different from the before too. The cold in here. Before we write it cold out, this one is cold in. So we put the info to the formula. Is 85 dBc minus with 30 dBc and got 55 dBc. So we must substitute all the information we got into the formula. And LMTD will be 45 dBc minus with 55 dBc divided by 1 times 55 dBc divided by 55 dBc. And we start the answer is 49.8 dBc. So after doing some calculation, we can get the answer for both parallel and counter flow heat exchanger. And that's all.
I will introduce you about NTU method. NTU method is the number of transfer heat. NTU is the ratio of the heat exchangers ability to transfer heat to the fluid's minimum ability to enter heat. It is also used to calculate the rate of heat transfer in heat exchangers, just like LMTD. NTU method usually used when there is lack of information in LMTD. Now, let us continue to the question that is related to the NTU method. So, this is the example of the question. It is said that water enters a counter flow double part HE at 38 degrees Celsius, flowing in the rate of 0.75 kg per second. So, 38 degrees Celsius is the temperature for the inlet for fluid, which is the water. So, this is the mass flow rate for the water flow. transfer rate, which is the symbol is Q. So this is the diagram, which is the cold fluid in the 38 degrees Celsius, and this is for the temperature cold fluid for the outlet, and this one is for the inlet, temperature inlet for the hot fluid, and this one is the temperature outlet for the hot fluid. So this is the calculation for the question. This is for the heat capacity for oil. This is the mass flow rate, and this is the specific heat capacity for oil. Then we calculate, we will get 2.82. Then this is for the specific heat capacity for water, which is the same formula, which is MCP water. Then we substitute the mass flow rate, which is 0.75. Then we multiply with the CP water, which is 4.18. Then we can get 3.14. Then for the heat capacity for both fluid, we have the lowest value and the highest value. So for the minimum, we have to take from the C1, which is 2.82, because it has the lowest value. So we use this formula to find the heat capacity ratio, C minimum over C maximum. So we will get 0.9. But this we don't have the limit, because we can cancel the limits for both of the C minimum and C maximum. Then after get the heat capacity ratio, we can substitute it in the NTU formula, which is UA over C minimum. UA is 340 times by 30, the area, then over C minimum 0.9. Then we can get 1.57. So it is given that for the effectiveness is 0.62. Then we can get for the Q, for the total heat transfer, for the effectiveness we have to multiply by C minimum, and for this one temperature, inlet for the hot fluid minus by temperature for the inlet cold fluid. Then we substitute all the values, we can get 136.41.
So let us continue to see for the next question, which is related to the NTU method. So question number 2 says that water enters across flow HE, both fluid unmixed at 16 degrees Celsius and flow at the rate of 7.5 kg per second to cool 10 kg per second of air from 120 degrees Celsius. So from here, we can get some information, which is TCI stands for temperature cold inlet for the water. Then we also have the mass flow rate 7.5 for the water. Then this is mass flow rate for the air, and 120 degrees Celsius is the temperature hot inlet, which is we denoted as THI. Then for an overall heat transfer coefficient of 220 W over m square Kelvin, and an exchange surface area of 240 meters square. So 225 is the U, then 240 meters square. Then draw the diagram like this. For the cross flow, we already have the 16 degrees Celsius for the TCI for the inlet, and for the outlet we just denoted as TCO. Then we already have 120 degrees Celsius for the THI here is the inlet and here is the outlet for the hot fluid. Then from the question, we already have the TCI, which is 16 degrees Celsius, THI 120 degrees Celsius, mass flow rate for the water, and mass flow rate for the air, and the overall heat transfer coefficient. CPL is given 1.014, CP water is given 4182, and the effectiveness is given 0.94. So since we have all the information, we can find the solution for these questions. Next, calculate the heat capacity for air by using this formula. So, mass flow rate for the air, which is 10 multiplied by 1014. This is for the mass flow rate of air, while this is for the specific heat capacity for air. Then we can get the answer 1014 W over K. Next, calculate for the heat capacity for water by using this formula. It's 7.5 is the mass flow rate for the water. 4182 is the specific heat capacity for water. Then we multiply both of these values and we can get 313,070 W over K. Next, since we have two values, this one is the lowest because this one is the has the lowest value compared to this one for the heat capacity of the water. So automatically the C minimum is the 10.14 kilojoule over SK. Then we use this formula to find the ratio of the heat capacity C minimum over C maximum. C minimum is the 10.14, then C maximum is 31370, and then we can get the answer 0.32. This one, we don't have the unit because unit is cancelled from this one. Then we can cancel both of these unit. Next, we can calculate the number of the transfer units by using this formula. This one, U times A over C minimum. U is the overall heat transfer coefficient, while the A is the surface area. Then this one is the C minimum. Then substitute all the values. Then we can get these values, which is 5.32. Next, calculate for the heat transfer, which is effectiveness times by C minimum and times by the temperature. Difference temperature for the hot inlet and for the cold inlet. Then we can substitute the effectiveness, which is 0.94, C minimum, which is 1014 W over K, then the THI 120, and the TCI, which is 16 degrees Celsius. Then we calculate, we can get this answer. After that, we can calculate the THO. Then the answer for the THO is the 32.6 degrees Celsius. Next, let us move to the next question. The question asks us to find the exit temperature of the helium and its mass flow rate. But let us take a look at for the whole question. First, the question says that hot water at 80 degrees Celsius enters the tube of two shell pass head tubes pass He at the rate of 0.375 kg per second, heating helium from 20 degrees Celsius. So at 80 degrees Celsius is the THI, temperature hot inlet. 20 degrees Celsius is the TCI, which is the temperature cold inlet. Next, the overall heat transfer coefficient is 155 and the exchanger area is 10 meters square. Overall heat transfer coefficient we denoted as U, but the area is A. Then, if the water is at 44 degrees Celsius, determine the exact temperature of the helium and its mass flow rate. Then we already have all the information. Next, move to the solution. We assume that Cp for the water is 4.185 kilojoule over kg/K. Then we calculate the heat capacity for water by using this formula. For the mass flow rate, we already have 0.375. Then for the specific heat capacity for water, we already have 4.185. We calculate and we will get the answer 1570 W over K. Next, use this NTU formula, which is UA over C minimum. So substitute the U with 155 and the area with 10 meters square over C minimum, which is 1570. Then we can get the answer, which is 0.99. Next, the effectiveness can be obtained by CH equals to THI minus THO over THI minus TCI. Then substitute all the values of the temperature, then we can get 0.6. Given that C is 0.25, then the C maximum is the C helium, which is 6280 W over K. Cp helium is 5.2 kilojoule over kg/K. So we can get the mass flow rate for the helium, which is 1.21 kg per second. Then we also can get the T helium for the out T helium, which is 29 degrees Celsius. So this is the final answer.
For my part, I will be presenting about Foley factors. Foley factor represents the theoretical resistance to heat flow due to the build-up of a layer of dead or other falling substance on tube surfaces of the heat exchanger. Few types of Foley factors. First Foley factors are chemical Foley. Chemical Foley is when chemical changes within the fluid cause a falling layer to be deposited onto the tube surface. For example, scaling in kettle or boiler caused by hardness salts depositing onto the heating elements as solubility of salts to reduce with increased temperature. Next Foley factor is biological Foley. This is caused by the growth of the organism within the fluid, which deposit out onto the surfaces of the heat exchanger. Other than that, there are corrosion Foley. This is when layer of corrosion products build up on the surfaces of the tube, forming an extra layer of usually high thermal resistant material. For example, we can choose corrosion resistant material such as stainless steel and other nickel based alloys.
I will tell you the maintenance of heat exchanger. So this is one of the type of heat exchanger. So let me tell you what is heat exchanger in short. So heat exchanger is a device used to transfer heat from two or more fluid. So in the heat exchanger, there are a lot of fluid coming in and out. So there will be contamination, loss of quality, and etc. To make the performance of the heat exchanger decrease. So we need to clean the pipe and tubes of various diameter and in the heat exchanger. Tube and tube bundles of heat exchanger need to periodically clean of scale and of sediment, rust, and everything, which lead to the reduce of productivity of technology equipment, and there will be a loss of final product quality. So that's why we need to maintain well the heat exchanger to their highest performance. There are a few factors that will reduce the performance of heat exchanger, which is cooling. What is cooling? Cooling is when the impurities deficit on the heat exchanger surface and deposition. These impurities can decrease the heat transfer effectiveness significantly over time, and they are caused by first, low wall shear stress, low fluid viscosity, high fluid viscosity, reaction product solid precipitate, and precipitation of dissolved impurities due to elevated water temperature. So, first thing is cooling, and second is crude oil exchange fouling. In short, the crude oil will time by time the crude oil will loss of their effectiveness due to some impurities coming mixed in the oil. Then by time we need to change the crude oil in the heat exchanger. Then cooling water fouling, which is susceptible to fouling. Cooling water typically has a high total dissolved solid content as suspend colloidal solid. So the cooling water, the cooling water also contaminate and make the performance of heat exchanger reduce. Then, so we need to maintain the heat exchanger to perform well. So we need full array of cleaning method that are capable of bringing the process equipment back to operational condition. So we need to maintain maintenance, which is we change the plate and frame heat exchanger and clean it periodically. One of the type of heat exchanger IP is turbulent heat exchanger, which is we can clean by acid cleaning, sandblasting, high pressure, water jet, bullet cleaning, and drill rod. For water cooling system, we need to such as purification. We need to purify the water, addition of chemical, and minimize and we will find a way to minimize the fouling of the heat exchanger equipment. To other water treatment also, we need to use steam system for power plant, etc. to minimize fouling and corrosion of the heat exchanger. So that's it. There is in short, that's it. That's how we maintain